what our plans are for the future, what other features we plan to put in. So that's sort of the thing here. So the question is, why make another executable compressor? Aren't the ones that are there good enough? And let's first look at the most common way of compressing 4K intros. So what most people did before Crinkler came along was to use this thing called cap dropping, which is this sort of three-step process, which is usually handled just by one program handling all of these things. So first you take your executable file, you run it in through this executable optimizer, which does some optimizations to the header and sets some things to 0 that can be set to 0, and sort of fiddles a bit with the executable, which makes it easily compressible. Then you feed it into the cap compressor, which is a built-in compression facility in Windows. So there's this cap compression, you can compress it, then you get this cap file, which can be decompressed with some Windows commands. But you can't run a cap file. So what people do is they insert something into the cap file and rename it to .bat instead. So when you run it as a batch file, the batch interpreter in Windows will find these commands that you inserted, which decompresses the cap file and runs the decompressed executable and deletes it afterwards again. So that's what's usually done. And I think one of the most popular programs that do this at the moment is the one called 20-4, which many people use. So what's the problem with this approach? So generally you would say this gives very good compression because you don't have to have your own decompression code. That's just in the Windows utility that decompresses these things. And you don't have to have the exe header. The header of the exe file is quite big, so this way the header can actually be compressed. So this gives quite good compression. But this dropping just causes all sorts of trouble. I mean, it writes it somewhere and it isn't allowed to write there because that file already existed, and then you run some other intro which happened to be there, or there's no write permission in the directory, maybe because you run it from a CD. And on my computer it never works because you just can't find this decompression program. So there are all sorts of trouble with this. So what we wanted to do is to make something that didn't rely on dropping, which simply just decompresses into memory and just runs the program directly, which doesn't have to write a file to the hard drive. We want it to be an exe file. So you just have an exe file, which is the 4K, and you run it, and the 4K runs. So that is sort of the goal. So it's a quite optimistic goal, right? Because you have to have the whole exe header and decompression code yourself. So the actual compressor has to be much better than the one used in cap for this to actually work, to give something that's competitive to cap dropping. So we did this in a slightly different way from the way you normally make executable compression. So normally what you do is you have your C or C++ files, you compile them, maybe you have some assembler files, and you put it all through an assembler. Then you have object files, and you take maybe some other object files you want to put directly in, and you link with some library files, put it through the linker, then you get an executable file, and you compress that using some compression utility. And you get out an exe file or a bat file or whatever. So what we do this differently is we sort of merge the linker and cruncher steps into one. And here you have the background behind the name of this program. So what it actually does is it's given a lot of object files and these library files, and it links them together and compresses the result. So why do that? Why make another linker? Why not just use the one that's there, which can produce an exe file for you? And the reason is that having your own linker gives much more control over how you can place the data. So when you have the object files, all the code and all the data are just lying there in sort of small chunks, which are not yet put into some specific locations in memory. That's the job of the linker. It sort of decides where in memory all these things are going to be put. and puts them together, and so the exe file is, in the exe file it has a specific base address where all the code and data is put, and it's the linker that chooses the base address. So by having control of the linker, we can choose the base address ourselves, which can in some cases be an advantage. And we can shuffle the data around, so there are many possibilities of how you can place this data. You can swap all these different functions around and swap all the data around, and some orders might give a better compression than others. So by having these, the control of this process in the compressor makes it possible for the compressor to try different orders and use the one that compresses best. And generally, when you're compressing something, you have to, or the best thing is to have similar data grouped together. So code and the other data you have in your 4K are very different, have a very different structure. So the compression is better if you put first all the code and then all the data. So Crinkler does that, so it separates that out. And you cannot be sure if you just use any other linker that the code and data will be separated. They could be sort of mixed in between each other. So that's also very, very important. And when we have this flexibility of moving things around, we can also put in extra code. And one of the things we put in is import code. I'll get back to that later, what that is. And you can do transformations. You have all your code and all your data, and maybe you can find some transformations you can do in the data to make them compress better. And if these transformations are very simple, then you can have the code doing the reverse transformation. You can just put it in first before the other code is run. And you couldn't do that if you just got an exe file, because there would be no space to put the code in, because you couldn't move the rest of the code. So that's why we did a linker. So the next thing is but just the linking thing in itself is doesn't sort of get us to the goal. We have to have a very good compression method also. So the thing that we use is called context modeling. So now I'll give a sort of a sales speech for context modeling. I'd say there's this fantastic thing called context modeling. This is this revolutionary compression method, which is compresses much better than this LZX, which is the method that the cap compression uses, and is well suited for small amounts of data like 4Ks, because it has a very small startup cost. It can begin compressing right away. In the LZX format, there's also a lot of tables and various things that have to be encoded first, the models about how the data is represented, before the actual compressed data. So there's a sort of a startup cost. So it's very good for small amounts of data, and it can be decompressed in not very much code, so it's less than 250 bytes. So that's a bit bigger than some of you might have heard of the APAC compression method, which is also very popular, which is a very simple compression method. So the decompressor there is much smaller than this, but this is so much better than that it actually pays off. Even with that extra header and even with the extra header, the compression is so much better that than on a 4K it ends out being smaller. And when I tell you all of this, you should actually be sort of skeptical, because if all of this is true for this great compression algorithm, then why doesn't every compression program use this algorithm? And then the answer is very simple. And no, it's not because it's patented or something like that. It's simply because it's extremely slow. So if you were to use this kind of compression for your normal archiving utility and so on, it maybe would be able to compress only a few kilobytes per second or something. So it could, or a few hundred bytes per second if you need to compress really well. So if you're compressing a megabyte, it takes a few days or something. So you couldn't live with that. But for a 4K, it's okay. I mean, it doesn't matter that it takes a minute or two to compress your 4K and maybe a few seconds to decompress it. So that's why it's okay to use an extremely slow algorithm for compressing 4Ks. It also uses a lot of memory, but a 4K intro usually uses a lot of memory anyway for storing all sorts of tables and music and whatever. So it doesn't matter much that the decompressor also uses a lot of memory, because you can reuse the memory for the actual intro. So that's also okay for that kind of thing. So that's why that's the sort of the point here is that 4K intros is such a special application that it using this general purpose compression that the cap compression does is not the best thing to do. It's better to have something really specialized for it. So I'll try to explain why this, what actually makes this context modeling better. And to do that, I have to go through some basic data compression stuff first. So what is data compression? Well, what does it do? What it does is it tries to take advantage of some self-similarity in the data. When you have some code or some data in your intro, there will always be some kind of patterns in it. Something that's data that is repeated, or some data comes more often than others, or the things that are aligned. You know, have sort of 4-byte wide data in a lot of places, and then you have sort of these structures, and code, executable code also has sort of built-in structure in it. So then all this structure can be used by the compressor to make it fit in a smaller space. That the two most common approaches to data compression are the ones called dictionary compression and statistical compression. So I'll try and explain what these are and what the difference between them. So first, dictionary compression, which is the most known. There is one called LZ77, which is the one used in LZX in some variant. In the most of the compression tools you use some variant of LZ77 with a lot of special cases and optimizations and things to make it better. But the basic thing is the same. That the point here is that when there's a repetition in your data, there's some block of data that you've seen before, you can replace that by reference back to where you saw it last. So I have this example, which is a classical data compression example, trying to compress the string Mississippi. So let's go through it from the beginning. M, we haven't seen an M before, so we just store an M. And the same for I and S. But then we see another S, so we can actually refer that back to the S that has just been. And it's a bit different from one variant of LZ77 to the next, whether it can refer like that, just 1 byte back and so on. But the principle is that you see something you've seen before, you can just replace it by a reference back. Then you see 4 characters which you have seen before. And it doesn't matter that the place where you saw it last actually overlaps with the place where you see it now, because when the decompressor comes around and decompresses, then when it reaches the last character, it has already decompressed the first one. So now it's suddenly 4 characters just by one reference. And P is not seen before. That P can be referenced back to that one, and the I can be referenced back to that I. So that is compression of Mississippi using dictionary compression, or LZ77 in this case. And so what's special about this? Why is this algorithm used so much? This is because it compresses reasonably well, especially if you put some other things on top of it and tweak it and make some special hacks in it. Then it can compress quite well. LZX compresses quite well, actually, generally for large amounts of data, at least. And it's very fast to compress, because it's just you just have to look back where you saw the things last, and you can use some clever data structures to find that. And it decompresses extremely fast, because the decompressor just reads this offset and goes back and reads the data and puts it in. So it's so that's why this method is used so much. So statistical compression, which is sort of the other way of looking at data compression, is completely different in its view on what needs to be done to compress the data. So the thing there is, each time you have to decompress or compress some symbol, which could be a character or byte or whatever, we try to estimate what is the probability distribution, which character is more likely to come here than others, and that can be based on what is seen earlier and what is seen just before this character and various things. So, but the basic thing is that you try to guess what the next character is, and the better the guess is, the smaller is the compressed size. There's a way to encode these things so that if you assign a larger probability to the symbol that was actually there, then it compresses better. So let's look at Mississippi again. So one of the most known approaches here is the one called PPM, prediction by partial match, which looks at the few characters just before the one that's going to compress, and then it sees if it has seen that sequence of characters before. And if it has, it guesses that the next character is probably one of those that follow the sequence last time it was seen. So we start at the beginning. We haven't seen anything yet, so there's nothing to guess from. So everything is given equal probability. The next place, we have seen an M, but we haven't, I mean, the context of the I, as you call it, if you look back, then there's an M, but we haven't seen an M anywhere before. So there's nothing telling us what should be here except what has been seen before in general of single symbols. And it's the same for all of these three. So here's here you still don't know. I mean, you haven't seen an S before this last one. But now the situation changes because the last character seen, so the context of where we are is an S, which you have actually seen before. So you can sort of guess that the character that comes now is probably the same that came after the last S we saw. So it's probably an S. Well, it isn't, so bad luck this time. But then the next one is, okay, so you are there, the context, when you look back, you see an I. You've seen an I before, and after that was an S. So this time it actually guesses correctly. So it guesses correctly that there's an S here. So now it actually compresses. And now it can actually find two characters it has seen before. So now it's really confident that the next thing must be an S. And now it's three characters. So, and as it sees more and more characters, it gets more and more confident that the next character is the same as before. So long repetitions will generally be compressed very well, which is the same as in LZ77, that long repetitions can be replaced just by a single reference back, so they will be compressed better. Here it guesses wrong again because it thinks there's an S coming now because that was the one after last time it saw this sequence, but it isn't. It's a P, and it doesn't know anything here. It hasn't seen a P before. Here it has seen a P before, so it's probably a P again. No, it isn't. It's an I. So you see, sometimes it guesses correctly, sometimes it doesn't. But actually, as you see, this compression sees the same kind of patterns as LZ77. It's all about sequences of characters occurring again, sequences that have occurred before. And this can actually, you can actually so it's a whole science how you estimate this probability precisely from what you're actually seeing. And you can do it in a way which compresses precisely as the LZ77 would have done. And you can also do it in better ways. So in general, this compression method is better than LZ77. But there's actually patterns that these compressions don't see. The problem is that it's local. It sort of looks at it only looks at the few characters immediately before where it's going to decompress. But it turns out there's another pattern here. That last arrow shouldn't be there. Just forget it. So when we are here about to decompress the last I, we see that 3 places back, that was an I. So we look further back in the data, see, okay, so where all the places where we have been were 3 places back, there was an I. what was the next one? And it turned out it was always an I. So every third character in this string is an I. But ppm can't capture this kind of pattern. And these kind of patterns actually occur quite often, especially in executable code. So the thing about the general context modeling as we use is that it can also capture these kind of patterns, not just the local ones. So it's a generalization of ppm in the sense that it can do everything that ppm can do, and it can also do more because it looks at combinations of recent symbols. So how do you sort of tell it which combinations it should look at? Well, you can describe such a model like looking 3 characters back by a bit mask. For instance, you could use 8-bit bit mask, which means you can look at the last 8 characters, and then in this case, you look 3 characters back, and you can actually guess that the next one is an I, because you have seen these 3 characters back 2 times before. So there's a problem with this, is that which masks do you choose? There are a lot of different masks you can choose. So in this 8-character example, if it's ppm, it has 9 different models to choose from not looking back and look 1 character, 2 characters, so on, up to 8. But in this case, we have 256 different models to choose from, because we can sort of turn on and off these bits individually. So you can't just take all of these models and look at those, because that would be horribly slow and use huge amounts of memory, and it wouldn't even compress very well, because you also have to keep track of which models are good and which are not as good. So that's a problem with this approach. But if you find some good models to use, then it can compress much better than the other approaches. So in the actual implementation, what we do is we estimate it not per byte, but actually per bit, because then we can also use the other bits in the byte we are compressing for the estimation, and that is a bit better. And it's also very simple to make the decompressor, so they decompresses 1 bit at a time. So the context that we're looking at is the current byte, and then the selection of the last 8 bytes determined by this bit mask. We have some algorithm in the compressor which tries to estimate what is the best collection of masks to use. So that's very difficult, because all these masks can be correlated. So if one is good, then another might be good, or you can have 2 that are good individually but don't contribute much to each other. They're not necessarily good together, and so on. It's very difficult. So we do some sort of approximate way of finding these, and this is actually a place where we think we might, as time goes on, come up with maybe some better things and improve the compression. But we do something, and then we try to estimate how you have a selection of masks, but you also need to know how much to trust in each of these models, and that sort of expresses how common these different patterns are in the actual data you're trying to compress. How common is it that the character you're decompressing is correlated to the one 3 characters back? And that determines how much you should trust in the mask that say just look at the character 3 characters back. So it's also something where you could it would take too long time to go through all possibilities, but we do some approximate stuff. You have to remember for all of these things. Remember basically everything you have seen for all of the models, all of the bit masks. You have to remember what are all the actual combinations of data you have seen until now. And an easy way to do that is to use a hash table. So calculate some hash value, some value from the last 8 bytes, or the ones that the mask selects. So calculate some sort of noisy function from that, and then look up in a table. And the problem with this is that sometimes these hash values collide. So you have the same hash value for 2 completely different contexts. So you sort of mix these 2 up in the compressor, which is bad, because then well, then it doesn't compress as good because it thinks it has seen the data before, and really it hasn't. Has seen something else. And what do we do about this problem? We ignore it. Because it turns out that if your hash table is sufficiently big, it's just a few bytes more that you lose by ignoring these collisions. And especially if you experiment a bit with choosing a hash table size where you are lucky to have few collisions, then it's not a big problem. So it's maybe 20 bytes you lose or something, which is much less than the code overhead would be of avoiding these collisions in the decompressor. So we try and look through a few sizes and find one with few collisions. So that's basically how we implement this algorithm. So the next thing, which is important for 4Ks, is function import. So in every executable file, there's a list of all the functions it uses in all the DLLs. So it has that. So for instance, if it uses OpenGL, it says that there's the OpenGL 32.dll, and from that one it uses all these functions. And these are listed as the names of the functions inside the executable file. So that import table is actually quite big. So the one important thing is to try to get rid of this import table. One thing you can do, which is just another thing you can do in the executable file, is to, instead of saying this name in this DLL, you can say function number 8 in this and that DLL. And the problem is that if you take that and run it on another machine, which has another version of the DLLs, just another Windows update, just another version of something, then the numbers are different, so it won't work. So that's very incompatible. Recent compa rules for 4K intros usually disallow this kind of import because it's so incompatible, but it has been used quite a lot earlier on. You can also do something quite different, which was invented some time ago, a few years ago, I think, that you can, instead of storing the number, you can store a hash function of the name. So compute some hash function of the name, and you just store that. That's maybe 4 bytes. We use 32-bit hashes. So what you do when you import is that you look through all of the functions in the DLL, and you find the one which has the same hash function. So it's still dependent on the name, not the number. So even if the numbers change, it will still work because the names are the same, so the hash codes are the same. And it's small because you don't have to have the whole names. It's not supported directly in the executable file format. You cannot just put the hash code there. So we have to have our own import code, which looks through the DLL and also all this kind of stuff. So as I said, we put that import code in the beginning of the file. Then we also invented a slight twist to this, which is something we call import by hashed ordinal range. Because in some DLLs, the ordinals of the functions are not quite fixed, but the only way they can change is that there can be added some other functions in the end or in the beginning. So the ordinals can change, but the relative ordinals between the functions will always be the same. That's the case, for instance, for the OpenGL DLL. So what we do in this case is we just store the hash code of the first function and then import a range of functions of the ordinals, so that all of the other functions can be imported relative to this hash function. So we only need to store one hash code, even though we're importing many functions from the same DLL. So that's only safe for some few DLLs, but it is for OpenGL, which is usually the one where you import most functions if you're using OpenGL in your intro. That was about function import. So the next thing is that the executable header is quite big. The normal header you get when you produce an executable file is this one, is 544 bytes. So that's quite a lot for a 4K intro. And there are different things in the header which mean different things. So the first one is the DOS header. because the exe file originates from the DOS days where there was this header with various information in it, and then after the header comes the code, and that's how a DOS exe looks. And Windows exe looks a bit different. It has in the end of the DOS header, it has this PE header offset, which is where in the file it can find the Windows header, which is called the PE header. And the Windows header has all various kinds of information about the executable that Windows needs to load the executable into memory. It has a section called data directories, which are pointers to various things in the executable, like the import table and also export table and other things. And then there's so the executable itself is split into sections, which are sort of the blocks of memory that will be allocated when it is loaded. And for each section, there's a section header in the header, and you have to have at least one section, so that section header is 20 bytes in the last part there. The DOS stop, the gray thing there, is the code that is run if you try to run this executable in DOS. So then it runs that code, and all that code does is it prints out a string which says this program cannot be run in DOS mode. And that's I mean, it's silly to have that kind of thing, because we don't care what happens when our file runs is run from DOS. So we can simply remove that one. So now the PE offset will point in a different place. It will point to the new place of the PE header. So we saved all that space for the DOS stop. And what can we do then? So it turns out that there's these data directories. These are these words you see there. Each of these is a pointer and a size, and there are 16 of these pairs. And it turns out that only 3 is needed. So the Windows XP or Windows 2000 loader only needs 3 of them to be there. So you can just remove the rest of them. So now we have a much smaller header. Then there are actually a lot of these fields in the header that the loader doesn't use for anything. It simply ignores them. And these are all the white ones here that are ignored. So maybe we could put something into these fields. It doesn't matter what's in there because they're ignored. So we can put anything in there. And one thing we notice is that this PE header doesn't actually have to be after the DOS header. It can actually start inside the DOS header. But then when it starts inside the DOS header, then the PE offset is still the same place in the DOS header. So then it has to end up in one of the ignored fields of the PE header. So it turns out that they can end up in this one. So we can move the PE header up like this. So we have reduced the header to 196 bytes. So there's still a lot of unused space in there. So what can we use that space for? In the case of cap compression, you usually just set all these things to 0 because then it compresses better. But we can do something better. It doesn't matter for us if we set it to 0 because the space is there. It has to be there in the final executable file. So what we do is we use it for hash codes. We have to store hash code for each of the imported functions, so we just store them in all the ignored parts of the header. So now we're down to actually having only 124 bytes overhead plus 18 hash codes. So if you use more than 18 hash codes, you can just put them after the header. And if you use less than, okay, then you waste a bit more space. But it's still, in most cases, it's only about that small amount of overhead. Okay, so it's time for the demo. So we have a small project here, which is 4K called A Little Shady. So we have this Visual Studio project, and let's try to build it to begin with. So what I've actually done here, which maybe you saw here, is that I've put as some post-processing step of this build, I've put compression by 20 to 4. So it compresses here, and we see that it compresses to 3,978 bytes. So you can ask 2024 to use ordinal imports. Then it is much better. It's down to 3,628. But then this is this very incompatible version, which probably only works on your machine, and if you're lucky, it works on a few others. So we don't really want to do this. So let's try and use Crinkler instead. So there's a special trick you can do here. So we want to replace the Visual Studio linker by Crinkler instead. So it runs Crinkler instead of running the linker. And unfortunately, Visual Studio doesn't have an option for replacing the linker by some other program. And what it does when it runs the linker is that it just runs link.exe. And then it's the first thing in the path called link.exe, which is run. So if we put, we have Crinkler here in the project directory. If we rename that to link.exe, then it will run Crinkler instead. So let's try that. So actually, if we just do it like this, there won't be any difference. So I'll just switch off the post-processing, so we won't run 2024 any longer. So let's try to build again. So the only difference here was that it prints out in this string here. It prints out the place where it actually found the Visual Studio linker. Because when you just run Crinkler with the normal linker arguments, it simply runs the real linker. So, because then you can put this link.exe in and use the real linker for testing and so on, and only use Crinkler when you're compiling for release. So we put in the project and properties here in the linker. We can tell it on the command line that it should actually run the Crinkler, and it is just an option called Crinkler. And it's an option that Crinkler sees, and that means that it shouldn't run the Visual Studio linker. It should run its own internal linker and compression. So we try and build again. So now it's a different output. It says what libraries it linked with. And here's actually a progress bar which is drawing the dots down there, but the Visual Studio console doesn't flush the output onto the end of the line, even when you tell it to flush it after each character. So it's only when you run it from a normal console that you can actually see this progress bar. So we don't know if there's any way to get around this. So as you see, it's compressing the code and the data in different parts. It's compressed completely individually because that gives a better compression ratio. And the last part is searching for hash sizes. So it has some maximum hash size, which is the default is 50 megabytes. And then it tries different sizes less than 50 megabytes to see which one actually gives the fewest collisions. So it tries to get the least size that way. So we see that the end result is 3,604 bytes, which is even better than 2024 with ordinal import. And this is with hashed import, so this is compatible. It will also work on other machines. So this uses hashed imports, but it doesn't yet use this hashed ordinal range import, because since that only works for certain DLLs, you have to tell it which DLLs it should use it for. So you can just put more options up here in the build script here. So you can say range OpenGL32, which means that when it imports from OpenGL32 the DLL, it can use range imports. And we'll try to build again. So there's actually We have two modes of compression. We have a fast mode and a slow mode, and this is the fast one. The slow one will take a couple of minutes usually to compress, and it compresses some maybe 20, 30 bytes better. So that's what you use for when you're making the final release, when you're compressing it in the end. And you can use this one for sort of judging the size while you're developing, and you can use the fast one. So let's see what the end result is. So if we saved another almost 100 bytes, 3519 bytes we are at now. And that's because all of these hash codes used for importing OpenGL functions is now just one hash code, or maybe it's two or something. There's a limit on how many functions it can import for each, but at least it's much fewer hash codes. So there's also some, it can also help you a bit in optimizing the size of this thing. So in the properties here you can, let's see, code generation, what was it? Or was it general? Debug information. So if we tell it to put in debug information, just anything here, it will put in information. So this just instructs Visual Studio to put in information in the object files about where each function in your code is and what it's called and so on. And Crinkler can use this information to tell you how much each code is compressed size, the uncompressed and the compressed size. So then you can actually see when you change some function is that if that function itself gets smaller. So let's see the output here. So there's this list. So there are not very many functions in this one, but it prints out the names of the functions, and you can see here the sizes and the compressed sizes, and then it's the bits per byte. So it tells you how good this code compresses. So you can, if you try to change something in the code, you can see the result directly for each function, how it's actually better. So that's helpful sometimes when you're trying to optimize the size. So I guess that's it for the demo. So just for completeness, we'll try to run the result, see that it actually works. So this is the file just produced by Crinkler, and it's doing a bit of pre-calculation. So we see it works. So so that was the demo. And the last thing is just a few words about how we intend to continue this project. At the moment, the files produced by Crinkler do not run on Windows 2000, and that is because we have our own import code, which means we don't need any imports at all in the executable file, so we don't have any. But for some reason, the Windows 2000 loader requires that there is at least one function imported for some reason. So we are looking at some ways to import some dummy function without wasting too many bytes doing that. So we know how to fix it, but not necessarily without wasting maybe 20 bytes or something. So maybe we'll make it an option to be Windows 2000 compatible. We can always find better ways of selecting these masks and doing other things to try and make the compression better. So we will continue trying doing that. And so I said one of the advantages of having your own linker is that you can reorder the code and reorder the data. We don't do much of that at the moment. We just pick one order which looks like it's good and then compress that. We split code into its own part and data into its own part, but on top of that we don't do much. So there's a lot of things you can experiment with there. Various transformations on the code. There's a thing like converting relative call offsets into absolute offsets, which usually makes your code compress much better. And the code for doing this, the reverse transformation, is quite small. So that's one of the things you could try and put in and see if it pays off in the end. And other kinds of transformations on the code. So for 4K, they have to be really good and with really small amounts of code for detransforming it. But some of transforms could actually be useful. So we'll try that out. Then you saw this thing with the feedback about function sizes. So there are probably many more kinds of feedback that would be useful. Like size of data, or what are actually the functions that are imported from DLLs. There are lots of things you could imagine that would be useful to have as feedback. So we'll put in more stuff. And we have some ideas for how we could use some similar techniques for compressing 64K. So you shouldn't try to use Crinkle on a 64K because first of all, the compressor will use a huge amount of memory for compressing it. At the moment, it requires 4,000 times the uncompressed size to compress a file, which is quite a big if your 64K is half a megabyte uncompressed, which is often is. And it is really specialized for 4Ks at the moment, so there are usually better things like Crunchy usually is better on 64K than Crinkler is. But we are thinking of some special things you could do in 64K. The thing in 64K is you can do very sophisticated things, especially you can do very sophisticated transformations to compress better, and we will experiment with that someday. So, but don't expect something soon in that area. So that's it. So if there's any questions or comments about it or suggestions of what we should put in or something? Yeah? Yeah? Yeah, so the question is how we can do the same feedback thing for data as for code, because for code the compiler could put in this debug information about where each function is placed, but it doesn't do that for data. So the answer is that one thing you could do is you could just take the labels of the data. So if each chunk of data is usually started by some label where you refer to the data. And you could just say that the size of it is from the label and then to the next label, or to the end of that section in the object file. So you could just list all the sections, all the data sections you have, and if you split your data into individual sections, then you can identify the individual sections in the linker, and then you can put out the compressed sizes of these. So this would be a way to identify the data. Okay.
So I was more thinking, when you do know, okay, I was compressing this function.
Yeah.
But I mean, it's how well it compresses depends on what I've seen before.
That's right.
So I mean, how reliable is it that to say that it gets this amount compressed?
Yeah. That's right. That the compressed sizes of the functions do not depend only on the function itself. It also depends on the data that comes before, and there's really nothing to do about that. I mean, it's just what you see is the compressed sizes of the function in the place where it is compared to the other functions. So one thing you can see is if you have two very similar functions, which are doing maybe the same thing, just one is having an add in some place and the other is having a subtraction, then you will very clearly see that the first one is compressing maybe not so good, and the second one is compressing very good because it can refer back to the first one, or it has learned these structures from seeing the first function. So it's right. It is the size in the context of the other functions that you see. Yeah. So any other questions? Yeah. Okay, so the question is, which of these optimizations we make and these techniques we use could also be used in things like 20 to 4 or for doing cap dropping, and so I think like hashed imports, it's difficult to do because there's nowhere to insert the import code, because when you have when you have it go from an exe file. You can't move the code and data around, so that you can't put in the import code in the beginning of the file. So you can't make hashed imports part of the compressor. You have to do it in your code yourself. You can make. For exe files, you could maybe, if you had your own decompression code, you could make it part of the decompression code, but then the import code is not compressed. One of the advantages of doing it this way is that the import code is actually compressed because it's just some part of all the other code that's in there. So the things like, you could use the same linker approach, and then this thing about trying different orders and splitting out code and data. You could of course use that as a front end for a compressor that then compresses using cap and drops it as a bad file. You could do that, and then you would of course gain something compared to 20 to 4. But I think actually the context modeling compression is so much better than LZX compression that it actually pays for having these decompression headers. So that's right. You would have fewer headers, but you would also not compress as well because the compression algorithm is not as good. Yeah. What? There will never be a Mac version. So of course this is very specialized for Windows exe files. All of these stuff are very, very Windows specific. So it's only for Windows. Yeah. You mean if hashing would work on Mac? I have no idea. I don't know how function import and that kind of stuff works on Mac. Okay.
Okay, thank you.